So what is the topic of today's lecture? So the topic of today's lecture is cache memory. Okay, what is a cache memory? Okay, so now I will explain the concept of cache memory. So before explaining the concept of cache memory, so what first we need to do? What is a computer program? A computer program consists of instruction and data. And where the instruction and data are stored. Anyone, please speak in mic. If you're speaking in mic and you're attentive, so I will give an easy example. Okay. Where these instruction and data are stored. So these instruction and data are stored
Base
in
register.
no, these instruction and data are stored in the main memory. Can you see? They
Main,
are main
yeah.
memory. They are stored in memory. Okay, so the memory stores instruction and data. Now, if you look at the memory, please look at the memory. What is a typical latency to access data from memory? Here, can you see here? What is the typical latency? Please, from 150 to 500.
500
Yes,
cycles.
yes, it's cycles. It's typically memory is very slow. So typically, if you look at the main memory, it is very slow. So it is very slow. It is very slow. And if you look at the register, now look at here. So the memory is very large. Memory is very large. It is very slow compared to the register. I will explain this with an example. So let's say if you have a library. In library, you have many books. Library is big. You can accommodate a lot of books in the library. But finding a book in library will take very more time. And registers. So let's assume this is your register, and register is, let's assume your table. And finding a book in the register is it's very faster because it's very near to you. So register is faster and memory is slower. Register is faster and memory is slower. Okay, how can we solve this problem? This problem can be solved by introducing a small memory. Okay, we call this as cache. And we introduce small memory between the processor and memory to bridge the latency gap between the slower main memory and the faster register file. So can you see here? So it is larger than the register, but it's much smaller than the memory. And what is the okay, in this example? What is the typical latency of a cache? Can you see? Can anyone tell me what is the typical latency of the cache in this example? Can you tell me?
4 to 10 cycles.
5 seconds. Okay, so it is bigger than register, but it is smaller than main. So I think let's assume we want to have some books in the library, and finding a book in the library will take more time, and finding a book on the table is very faster. But when we put a book rack, this is just like a book rack. This is faster than register and slower than memory. Any question? Should we proceed? What is the purpose of the cache? So the purpose of the cache is to accelerate the system performance by storing frequent access data closer to the processor. Okay, now if we look at here, this is so the program of an access data that is stored in the memory contiguously. Now, if you look at this code, please look at this. Which code is this? Can you tell me which code is this? Help me, please. Which code is this? Please help me. Please speak in mic. I want the section to be more interactive. Yes?
C, Java.
C++ code. Okay. Now, can you see this is C++ code? Okay. Okay. Now, if you look at here, so now program of an access data that is stored in the memory contiguously. Now, it is stored in the memory contiguously. Now, we have an array. Please look at here. We have an array. Now, this is an array A. This is an array A. And array like A in the code on the top is stored in the memory contiguously. How many elements are there we are accessing from the memory? Please look at here. Now, this is the variable K. So, okay. Now, if you look at this code, so we are accessing 12 elements of the memory. We need to access A0, we need to access A1, we need to access A2, we need to access A3, and so forth. So basically, we need to access 12 elements from the memory. Any question? Okay. Okay. Now, for the above code, we need to access 12 elements from the main memory because this is the condition K smaller than 12. So we need to access A0, then we need to access A1, A2, A3, and blah blah blah. And we assume, okay, now this is our assumption. Now this is my assumption. We assume that it takes 200 clock cycles to access one item from memory. So to access one item, how many clock cycles are required? 200 clock cycles. This is my assumption. This is my assumption. Okay, now to find the sum of all elements of the array, first we need to access A0, then we need to access A1, then we need to access A2, and blah blah blah, and then we need to access A11. Okay, how many clock cycles will be required to access all elements of the array? How many clock cycles? 24 clock cycles. To access one item, we need 200 clock cycles. But to access 12 items, we need 12 multiplied by 200, so we need 2400 clock cycles. Any question? Any question? Should we proceed?
Yes, Professor.
Okay, now in the next slide, we'll explain how can we reduce the latency by introducing the cache between the faster processor and the slower memory. Okay, I will explain this in my next slide. Okay, now the data in memory can be logically organized into blocks. Okay, now if you look at here, now we have logically organized. Can you see it? We have logically organized the data into 3 blocks: BI, BJ, and BK. Okay. We assume that the block size. What is now the block size? It consists of 16 bytes. What is the size of each element? The size of each element is 4 bytes. So the size of A0, we assume that it is an integer. So the size of A0 is 4 bytes. The size of A1 is 4 bytes, and it's a byte addressable memory. So if it's a byte addressable memory, so we assume that the size of the block size is 16 bytes. And each block has been assigned a unique tag, which is calculated from the main memory address using this formula. Okay, now please look at here. Now each block has been assigned a tag. What is the tag for block BI? What is the tag for block BI in this example? 400. What is the tag of block BJ, which is the blue color, which is actually 401? And what is the tag of the third block, which is actually 402? Okay. Okay. Now this is now the block tag. What is the block tag of BI, which is 400? All these block tags are in hexadecimal. The block tag of block BJ is 401, and the block tag of block BK is 402. Now what we are going to do? Now we are going to introduce a smaller cache between the processor and the main memory. And what is now the latency of this cache? Yes, can you not tell me what is the latency of this cache? Help me.
4 cycles.
4 cycles. What is the latency for main memory? Help me.
200 cycles.
200 clock cycles. Okay, now we want to fetch all elements one by one. Initially, we need to access A0. Okay, this A0, please look at here, this A0. What is the address of A0? Can you tell me what is the address of A0?
4000.
4000.
400. Yes. What is the address of A1?
4004.
4004 and so forth, so on. Because the size of each element is 4 bytes. We assume that the size of each element. And this block size is 16 bytes. Okay. Initially, we want to access A0. We want to access A0. Oh, we assume that one cache access is 4 clock cycle. So we assume a cache with 4 entries. How many entries are there? This is the first entry. This is the second entry. And this is the third entry. And this is the fourth entry. So we assume that there are 4 cache entries. And each cache entry has 3 fields. What is the first field? Valid bit. Valid bit is this thingy. The tag bit, it stores the tag of the main memory block, and this data, it contains the data, a copy of the data from the main memory block. Okay. What is the valid bit tells me? The valid bit tells me that now the data in the cache is invalid. So we have 4 entries. So all of these 4 entries are valid or invalid? Please help me. You can speak in mic. Yes. Are these 4 entries are valid or invalid? Please speak in mic. Because the valid bit is 0. These are valid or invalid? Anyone may speak in mic, please. Do you hear me?
Yes, Professor.
Okay, please speak in mic. I want your attention. Speak in mic. All these 4 entries valid or invalid? These 4 entries. Help me.
Invalid.
Invalid.
All of these are because initial. Okay. Now, first we need to access A0. We need to access A0. We need to access A0. Okay. This A0 belongs to which block? BI, BJ, or BK? Anyone tell me? A0 belongs to which block?
BI.
Belongs to BI. It is this block BI is in the cache or no? Is it present in the cache or it's not present in the cache? Initially.
It's not present in the cache.
It's not present in the cache. So what we need to do? So actually, so BI is not found in the cache. It's a miss in the cache. Okay, we miss in the cache. What we need to do? So we not only bring A0, but we bring the whole block from the main memory and load it into the cache. Okay, so now can you see here, we bring the whole block. So the block BI is now brought from the memory. Okay, now please remember, this A0 now belongs to block BI. This A0 now belongs to block BI, and it's not present in the cache. So we not only fetch BI, but we bring the whole block from the memory. Okay, what is the tag for this block BI? What is the tag for block BI? 400. This is 0x400 is the tag of the block BI. So we set the valid bit to 1, or it means now the cache contain a valid entry. Okay, the tag of this 400 is now placed in the tag field, and we fetch the whole block. We not only bring A0, we also bring the whole block to which this A0 belongs. This A0 now belongs to BI, so we bring the whole block. So we bring A0, A1, A2, and A3. Okay. Now, in the next iteration, we need to access A1. Okay. Now, A1 belongs to which block? Help me. Help me, please. Please speak. A1 now belongs to block BI. Very good. It belongs to BI. Okay. Now, what is the tag? This tag matches or not matches? So this tag matches. So it's found in the cache or not?
Yes.
It's found in the cache. So now it's found in the cache. It's a hit in the cache. How many clock cycles it will be required to access this from the cache? 200 or 4 clock cycles? 200 or 4 clock cycles? Help me. For A1.
4.
4 clock cycles. So it will be found in the cache. It will be accessed much faster. Next time we need to access A2, and this A2 now belongs to block BI, and because the tag matches, it's a hit in the cache. Its latency is served with much faster. And similarly, if we want to access A3, it belongs to block BI and faster. Okay. In the next iteration, we need to access A4. It's a hit in the cache or miss in the cache. It's a miss in the
It's a
cache.
miss.
It's a miss in the cache because what is the tag of block BJ? The tag of the block BJ is 0x401. It's 401. It's not found in the cache. What should we do? We bring the whole block. We not only fetch A4, but we fetch the copy of the block A4, A5, A6, and A7. The valid bit is set to 1. The tag, now the tag, this is 0x401. The tag is this thingy. Now the tag is here. And now we bring A4, A5, A6, and A7. In the next iteration, we need to access A4, A5, A6, and A7. Will it lead to a cache hit or a miss? A5, A6, and A7. Because A5, A6, and A7 belongs to block BJ and it's found in the cache, so it will be accessed much faster. So these will lead to a hit in the cache. And the same thing will be true for A8, A9, and A10. Okay. Now we see. Okay. Now how? Initially, we are now accessing A0. It's a miss in the cache. The latency to access the data from the cache is 4 clock cycle. From the memory, it is 200 clock cycles. So the total latency is now 204 clock cycles. In the next iteration, we are accessing A1. Now it's found in the cache. So the data is now accessed much faster with a latency of 4 clock cycles. And similarly for A2 and A3, they are hid in the cache. Then we access A4, which belongs to block BJ. Initially, it is not found in the cache. So we bring the whole block, and the latency to access the data from the memory is 4 cycle is the latency to access the data from the memory, and 200 clock cycle is the latency to access the data from the main memory. And A5, A6, and A7 will be hit in the cache, and we access this data much faster. And similarly for A8, initially it's a miss in the cache. It will take more clock cycles, and A9 and A10 and A11 it will hit in the cache. So if we calculate the overall latency, if we compute the overall latency, and if we compute this thing, so the total latency to anchor to access all the elements of the array is now how many clock cycles? How many? 648 clock cycle. 648 clock cycle. And actually, now we have reduced the latency. We have reduced using cache. We have reduced the overall latency to access all elements from the array is now reduced from 2400 clock cycle to 648 clock cycle. Any question? Any question? Should I proceed? Should I proceed?
Yes.
Yes, Professor.
Yes.
Yes.
So now what's now cache? Cache is now based on the principle of locality, namely a special locality and temporal locality. What is a special locality says? The special locality, the principle of special locality says that if we access one if a program accesses one memory address, there's a good chance that it will also access the other nearby addresses. So it means that if you are accessing A0, it is more probable that we will access A1. And if you are accessing A1, it is more probable that we will access A2. So this is a principle of special locality. Array is a classical example of a special locality. So it says if you are accessing A0 now, it is more probable that we will access A1 in the near future. And if you are accessing A1, it is more probable that we will access A2 in the near future, and so forth, so on. So for this reason, whenever we are fetching any item, and if it's a miss in the cache, we not only fetch the item, but we fetch the whole block from the main memory. And what is the principle of temporal locality says? The principle of temporal locality says that if a program accesses one memory address, there is a good chance that it will access the same address again and again. If you look at this code, so can you see here this variable sum? This sum is accessed multiple times, and this k is also accessed multiple times. What is the initial value of k? Initial value of k is 0. Then we are accessing the next value of k is 1. The next value of k is 2. So we are accessing this k, and we are also accessing this this sum multiple times. This is the principle of temporal locality. So what does the because both of these variables, both the sum variables and the k variables, is accessed multiple times. So the temporal locality says that if a program accesses one memory access, it is a good chance that it will access the same address again. So in this particular example, if you are accessing k now, it is a good chance it will access k again. So what is the classical example of temporal locality? So the classical example of temporal locality is the loop variables, because a loop variable is accessed multiple times. Any question? Any question? Should we proceed? Please speak in mic.
Clear.
Is it clear?
Yes, Professor.
Okay, good. Okay, now, and special locality also exists in programs. Now, can you see here? This is my, please remember, this is my C program, and now this is my assembly program. Please remember, it is not an LC3 assembly. This is just like another assembly. Okay, now if you look at here, this is my C program, and this is my assembly program. How many instructions are there in the assembly program? Can you not tell me? 1, 2, 3, 4, 5, 6, 7. So can you see now? This program consists of 7 instructions. This is an assembly program. This consists of 7 instructions. Okay, all these instructions are stored in the main memory. All these instructions are stored in the memory. Okay, now this is the starting address of the first instruction. So this is the first instruction. This is the first instruction. We assume that the size of each instruction is 4 bytes. What will be the next address? Can anyone tell me what will be the next address? So this instruction will be stored into the memory at the address of BC00. Since the size of each instruction is 4 bytes, what will be the next address? The next address will be BC04, because we assume that the size of the instruction is 4 bytes. So now the second instruction will be stored here. What will be the address of the next instruction? It is BC08. We are adding 4 to it. So this is the third instruction, and so forth, so on. So all of these 7 instructions, are now stored in main memory. Okay, so special locality also exists in program, and typically the instructions are executed in sequence. So if we execute an instruction 1 now, it is more probable that we will execute the next sequential instruction. So this is called as the special locality. So the special locality says that if we are executing an instruction 1 now, it is more probable that we will execute the next instruction in sequence. Any question? And what does the temporal locality says? The temporal locality also exists in program, because the loop body will be executed many times. How many instructions are there? So these are 4 instructions: instruction 4, instruction 5, instruction 6, and 6, and so on. And because now this is now the loop variable, and all of these instructions will execute how many times in this example? In this particular example, all of these instructions will execute 12 times, because the loop variables. So all the instructions which lie within this loop will be executed multiple times. So first, okay, in the first iteration, we'll execute I4, then I5, then I6, and then I7. And then we'll fetch again I4, I5, I6, and I7. Is it temporal locality or special locality? Yes, it is temporal locality, because we are executing the same. Okay, now if you are executing instruction 4 and then we are fetching instruction 5, this is special locality. Okay, then we are executing instruction 6. special locality. Then we are executing instruction 7, special locality. We move back to instruction 4. So instruction 4 is reused again, so it is temporal locality. Any question? Any question? Any question? Should we proceed?
Yes.
Okay. Okay, now, here is now the general organization of the cache. So here's the general organization of the cache. Okay, now, we have the main memory byte address. Now, this is the whole main memory byte address. This main memory byte address can be partitioned into 3 fields. The first field is the tag field. The second field is the index field. And the third field is the offset field. Okay? And how will it look like? So now, please remember. So now if we have this thingy, so now the cache consists of how many sets? So the cache consists of S sets, starting from set 0, set 1 until set S minus 1. So the cache consists of S sets. And how can we compute S? S is actually 2 to the power k. S is 2 to the power k. Here's the general organization of cache. Each consists of a cache line. So it consists of cache line 0. So this cache line 0, cache line 1, and so forth, so on, and cache line. So each set consists of a cache line. And each cache line consists of 3 fields, and we discussed it earlier. The first thing is the valid bit. The valid bit indicates whether the data in the valid, a particular entry in the cache is valid or not, and the tag field is store the tag of the main memory block address and the block data field. So we have how many bits are required for the tag field? We require t bits for the tag field. And how many bytes are there in the main in a block? So these are d is equal to 2 to the power b bytes per cache block. So this is the cache size. So what is now cache size? S, there are S sets multiplied by A, because there are S sets. Each set consists of A cache lines, and in each cache line we are storing d bytes. So this is the cache size. And I will explain this in an example. So this is a simple example. Please remember, this is a simple example. Now we have a byte address. Can you see here? Now this is my byte address. This byte address is partitioned into now 3 fields. The T field, which is 4 bits, the K fields, which is 2 bits, and the B field, which is the block offset field, which is shown in the red color. Okay, now please remember for this example, how many sets do we have? We have 2 to the power k. Now which k here? Now k is 2 here, so now we have 2 to the power k, which is actually 2 to the power 2. How many sets are there in this example? There are 4 sets. So these are 4 sets. There are 4 sets. So this is the set 0, set 1, set 2, and set 3, because it depends on k. What is k? K is 2. So we have now 4 cache sets. Okay. Now each set consists of 2 cache lines. This is cache line 1, and now this is cache line 2. Now if you look at here, there are how many bits are used for the tag field? So for the tag field, there are 4 bits, which is shown in blue color. Okay, now each block now consists of 2 to the power b. This is 2 to the power b. So this is actually 2 to the power b, which is actually 2 to the power 2. So now there are 4 bytes. So now the block size is now 4 bytes. So now we need to answer 2 questions. This is very important. We need to answer 2 questions if you want to map any data point. How do we know that if the data item is in the cache? The second question, and how do we find it? And now we need to define the cache data mapping. That determines that how particular data item, which is actually the byte from the main memory, is mapped to a specific location in a cache. And I'll answer this question in my next slide. So can you see? Now this is a cache. Is a small cache. Okay. Now can you see here? Now what is now my byte address M? So the byte address consists of 8 bits. 4 bits are required for the tag field. 2 bits are required for the index field, and 2 bits are required for the block offset field. And if you combine all of them, so these are 8 bits. What will be the memory size? So now my memory size will be 2 to the power M. What is M here? M is 8. So how many bytes will be there in memory? So there will be 256 bytes in memory. Okay, this is 256 bytes in memory. Can you see here? Now there are 256 bytes in memory. Okay, now all of these 256 bytes. What is now my block size? Okay, now please can you see here? Now the red color. Please remember, now this is the red color. The red color now shows me the block offset B bits. The black color now tell me the set index K bits. And now the blue color shows me the tag field. And how it will work? Now, what is now my block size? So the block size is actually 2 spot B, which is actually 2 spot B, and B is 2. So 2 spot 2, which is actually 4. So there are how many bytes in a block? There are 4 bytes within a block. Okay, there are 4 bytes in a block. So how many number of blocks are there? So the number of blocks can be calculated by dividing the memory size. The memory size is now 256 bytes. What is my block size? Block size is now 4 bytes. So there will be how many main memory blocks? So there will be 64 main memory blocks. Can we see? So there are now 64 main memory blocks. Now what we are going to do? So these 256 bytes are now logically partitioned into 64 main memory blocks. So this is main memory block 0. Please remember, now main memory block 0. Which color? This is now the gray color. Okay. Now this is main memory block 1. Each memory block consists of how many bytes? Each main memory block consists of 4 bytes. So main memory block 0 consists of 4 bytes. Byte 0, byte 1, byte 2, and byte 3. This is main memory block 0. This is main memory block 1. And since there are 64 main memory blocks, so this is now main memory block 62. Main block 62 consists of byte 248, 249, 250, and 251. And the last main memory block 63 consists of 252, 253, 254, and 255. Okay, now this is now my main memory block 0, and the last block is main memory block 63 now. Again, please look at here. Now, if you look at the most significant bits, so now this is my block address, block 0 address. What is the address of block 0? The block 0 address is 000. This is block 0 address. This is now block 1 address. And the block address can be computed by concatenating the tag bits and the index field. And now this is my block 62, and now this is my block 63. If we convert, please remember, so this is the block 62. If we convert this block 62 in decimal into binary, it will give me 111110, which is actually block 62. And now this is my block 63. Okay, now how many blocks do we have in memory? Now, for this particular example, we have 64 memory blocks. So can you see here, this is memory block 0, which contains byte 0 to byte 3. Memory block 1 contains byte 4 to byte 7. And memory block 62 now contain byte 242 to byte 241. And this is memory block 63 contains byte 252 to byte 255. Okay, now please remember, now we have some field, index field. The index field is now shown in the black color. And now we have the tag field. The tag field is now shown in the blue color. Okay, now this is now index field, which is actually K. How many sets do we have in the cache? So we have tools for K sets. How many sets do we have? Set 0, which is actually the index field. So the set index is 00, 00, and 01, and 10, and 1. Okay, now see here. Now, if you look at here, now this is main memory block 0. Block 0 is now mapped. Now we showed that how the main memory block is mapped to a particular set. So the block 0 is mapped to set number 0. Where should block 1 should be mapped? Anyone help me? Can you understand? Where should block 1 should be mapped? Anyone may help? Are you listening? Hamdan?
Yes, Professor.
Yes, please answer me. Memory block 0 is mapped to which set? Set 0.
1.
And block 1? Set 1. Block 2? Set 2. Block 3? Set 3. What about block 4? Where should block 4 should be mapped? Help me. Anyone may help. Yes.
Set 0.
Yes. Yes, very good. So block 4 should be mapped to set 0. Block 5, set 1. Block 6, set 6. Block 7, set 3. Where should block 8 should be mapped? Block 8. Where should be memory block 8 should be mapped? Help me. Please remember, we are not showing all the memory
0.
blocks. We are showing only some. Huh? Block
Is
8.
it 0?
Yes. So block 8 should be mapped to set 0, block 9 should be mapped to set 1, block 10 should be mapped to set 2, block 11 should be mapped to set 2, and so on, so on. So now I'm putting up dots here. Okay, where should block 60 should be mapped? Yes, block 60 should be mapped here. Help me. Block 60.
Is it based on the tag?
No, it's based on the index. It's based on the index.
It's 0
Can
again.
you see here? So can you see here? Block 60 should not be mapped to set 0 because it's based on the index field. Block 61 is mapped to set 1, block 62 is mapped to set 2, and block 63 is mapped to set number 3. Okay, now please look at here. Now please look at here. All the blocks which are mapped to set 0, what are the blocks which are mapped to set 0? All the blocks which are mapped to set 0 are MB0, this block which are shown in this the gray color. Block 4 is mapped here, and then block 6 is mapped here. And if you look at all the memory blocks, all of these main memory block has the same index field, and that index field is 0, 0. So this is 0, 0, 0, 0, 0, 0. So it means mapped to set number 0 because it has 0, 0. Any question? Any question? Okay. Now, what about all the blocks which are mapped to the same sets? So can you see memory block 0, memory block 4, memory block 8, and memory block 60? They have the same index field. They have the same index field. Okay. Now, all the blocks which are mapped to set number 1. So the blocks which are mapped to set number 1 are what? Memory block 1, memory block 5, memory block 9, and blah 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 until memory block 61. So can you see here? All the blocks which are mapped to the same cache set has the same index. What is the index of all these blocks? Help me. 0, 1, and 0, 1. And 0, 1 means it is set number 1. Any question? Should we proceed?
Yes.
Okay, now what do you do? Now what we are going to do? Now all the blocks, now please remember, all the blocks which are now mapped to set number 0, they have the same index field, tag field or different tag field. Help me. Look at the black color. Can you see the pattern? Can you see here? Now, the main memory block 0. So this is block 0. Block 0 is mapped here. Block 4 is mapped here. Block 8 is mapped here. 8 is not shown here. And block 60 is mapped here. This is block 60 is mapped here. Do they have the same tag field or different tag field?
Different.
They have different tag field, but they have the same index field or different index field. Help me.
Same.
Index is same, but the tag is different. Any question? Okay. Now can you see all the blocks which are mapped to the same set has different tag field, but they have the same index field. Again, now if you look at here, main memory block 1, block 5, and block 61 are on mapped to set number 1. They have the same index. The index is 0, 1, 0, 1, and 0, 1. Do they have the same tag or different tag? Help me.
Different.
They have different tag. So the tag is 0, this tag is 1, this tag is 2, and blah blah blah. And this tag is 1, 1, 1, 1. So all the blocks which are mapped to the same cache set has different tag field. So what is the tag for MB1? It's 0, 0, 0. What is the tag for MB5? MB5 0, 0, 0, 1. And what is the tag for 61? Block 61, it is actually 1, 1, 1, 1. Any questions? Should we proceed? Now can you see here? Now what we are going to do? Now I'm going to show you another example. Okay. Now can you see here? Now please remember we are revisiting our thing. Now what is my memory size here? My memory size is choose for M, which is actually here. M is 8. There are 256 bytes. So these are 256 bytes. And now let's assume we are looking at any arbitrary byte. Can you see here? So this is actually now if you look at here, how many bytes are there in the main memory? There are 256 bytes, starting from byte 0 to byte 1, byte 2, and blah blah blah. Then we have byte 254 and byte 255. So there are 256 bytes in main memory. Okay. Okay. How many number of memory blocks will be there? So with the memory size, the memory size is 256. Now the block size is 2 for 2. There will be 64 main memory blocks. So this will be 2 for 2. So these are 64 main memory blocks. Okay. Now please remember, byte 0 and byte 1 belongs to main memory block 0, which is shown in this gray color. Okay. Now if you look at here, the blue color, byte 254 and byte 255 belongs to main memory block 63. It will contain from byte 252 till byte 255, which are not shown here. Okay. Now if you look at here, this byte 136, 137, 138, and 139, they belongs to which memory block? It belongs to main memory block 34. How? I will explain it. Now, can you see here? Now, if you look at here, if you convert this number, please look at here. If you convert this number, this is my number. So this is converted in binary. So this is my binary. This is 1000 and then 10. So the tag is now 1000. The tag is now 1000. The index is 10, and the byte offset field is 01. If you convert this number into binary, into decimal, it will be 137. So can you see here? If you convert this number, this okay. Now can you see here? This is my byte address now. Can you see? This is my byte address. This is my byte address. The byte address is 100010. Please look at the color coding. The blue color stands for the tag. The black color takes for the index, and the red color stands for the offset field. Okay. So now this is the address. This is the address. And now this is the byte ID. 137 is the byte ID. So if you convert this thing, if you convert this binary number into decimal, it will give me the byte ID. Okay. Now can you see here? Now this byte number 137, according to this thing, byte number 137 now belongs to which block? It belongs to block number 134. How? Let's see. Okay. So now byte number 137 in this example belongs to main memory block 34, which is the second byte. This is the second byte. This is the first byte. This is the second byte. This is the third byte, and this is the fourth byte. This is the second byte, which is actually byte number 1 within the main memory block 34. And how do we compute this block number 34? Okay, so we concatenate the tag bits and the index field. So when we concatenate the tag bits and the index field, so if we convert this number, so what is the tag bits? So tag bits is 1000 and the index field is 10. If we convert this number into binary, it will give us 34 in decimal. So it means that the concatenation of the tag bits and the index bits will give me the main memory block number. So this is the main memory block number. So can you see here? So now this is, if you convert this into decimal, so it will give me the main memory block 34. Okay. Now, what does the index field tells me? What is now my index field? So it means now the index field indicates to which set this block belongs to. So it means 10. If you convert this into decimal, so it's actually 2. So it means that the above address is now mapped to set number 2 of the cache. If it is 10, it is mapped to set 2. If it's 11, it is mapped to set 3. If it is 00, it is mapped to set 0. If it is 01, it is mapped to set 1. Clear? Okay. Now, the offset field indicates which byte number is in the block. So it is actually the byte number. If you convert this 01 into decimal, it will give me 10. So this is actually, it is 01. And it means that we are now accessing the byte number 1, which is the second byte within this main memory block. Okay. Now the tag field determines whether this main memory block 34 is present in set 2 by comparing it with the stored tag field. And I'll explain this in my next slide. So in this example, we have 64 memory blocks, and okay, in this particular example, how many memory blocks we have? So we have 64 memory blocks, and how many sets are there in the cache? So we have to for 2 because k is now 2. So there will be have 4 sets. Now can you see? Now we have 4 sets, starting from set 0, set 1, set 2, and set 3. Okay, which block will be mapped to set 0? Main block 0. Main block 1 is mapped to set 1. Block 2 is mapped to set 2. Block 3 is mapped to set 3. Then 4 is mapped to set 0. 5 is mapped to set 1. 6 is mapped to set 2, and 7 is mapped to set 3, and so forth, so on. Okay, now if you go for this, so main block 32 is mapped here, 33 is mapped here, and so forth, so on. So can you see here? Okay, how many tag fields are there? So please remember, now we have t is equal to 4 here. T is equal to 4. So there are 4 bits for the tag field. So how many main memory blocks can be mapped to a particular cache set? So it means 2 for t, which is actually 2 for 4, which is actually 16 main memory blocks can be mapped to a particular cache set. How many memory blocks can be mapped to a particular cache set? 2 for t, which is actually 16 memory blocks can be mapped to a particular cache set. And how many of them can reside? Only 2 can reside, because now associativity is 2. 2 can reside in the cache at one time. What will be the tag for the first block? The tag for the first block will be 0, which is actually 0000 in binary. The tag of the second block will be 1, which is actually 0001 in binary, and so forth, so on. And what will be the tag of the last blocks? Since there are 16 blocks which can be mapped to a particular cache set, so the tag of the last block will be 1, 1, 1, and 1, because there are 4. 4 bits are dedicated for a particular tag. Okay, now how it works now. So can you see here? Okay, now please remember, and we did it previously. Now this is byte number 137, and please remember we already did it. This because this byte number 137 now belongs to main memory block 64. So first we need to look into the index field. Index field means 10, and 10 means it is mapped to set number 2. Okay, this is 00, this is 01, this is 10, and this is 1. So this is mapped to set number 2. We are now accessing set number 2. And then we compare the tag field. Can you see here? Now this is now my tag field. We are comparing this tag field with the stored tag field. These are two tag fields. One is in gray color and one is in pink color. So if you look at here, so now we are comparing this tag with these two tags. Okay. Now if you are comparing this, the tag of the incoming byte address with the stored tag, it is 0010 and 11. Which tag matches? The first tag matches or the second tag matches? Can you tell me? The first tag is matched or the second tag is matched? Can you tell me?
Second.
The second. So can you see here? Now block 34 is now finding the sec 2. And please remember, so this is a hit in the case. So this tag is matched with this tag, so it's a hit in. And now we are using the block offset field. If you look at the block offset field, it means it is 01. When it's 01, it means we are accessing byte 1 of the main memory block byte 34. So we are accessing the byte 1, which is shown in this red color. We are accessing this byte. So what we are going to do, we are now accessing the byte 1. Any question? This is one example. Now we will do some more example. Okay. Now this is example number 2. Please remember. Now the first one was example number 1. Now I am doing example number 2. Now we have example number 2. Please remember this is another example. This is another example. Now here, how many bits are required for the byte address? These are 8 bits. Can you see? These are 8 bits. 4 plus 2 plus 2, which is 8 bits. Now in this example, how many bits are total there? What is T now? T is 4 now. Index is 5 bits. And the block offset field is now 6 bits. Okay. Can you see here? How many sets will be there in the cache? So we have choose for K. Now in this case, K is 5. So now we have choose for 5 sets. So it starts from set 0, set 1 until set number 2. So if for this particular example, we have now 32 sets in the main memory. Starting from set 0 and it will goes to set number 31. How many lines are there in each cache? How many lines are there in each cache? In this particular example, how many lines are there? Please help me. How many lines are there?
2.
There are 2 cache lines. How many bits are required for the tag field in this example? These are
4.
4 bits per cache line. 4 bits per cache line. Okay. Now if you look at here, okay, how many? What is now the block size? The block size is now 2 for B. How many bits are required for B? So it is actually 6 bits are dedicated for the block offset field. So it means here will be 2 for 6, which is actually now the block size is 64 bytes in this example. So this is 2 for 64 bytes. Okay. Now what is the cache size? Cache size is equal to S multiplied by A multiplied by D. What is S here? S is now 32. A, there are 2 cache lines per set, which is 2. And what is the block size? The block size is now 64 bytes. And if you calculate this, so now the cache size is 4 kilobytes. What is now the memory size? The memory size is actually 2 for M. M is now 15 here, 2 for M, 2 for 15. So the memory size is now 32 kilobytes. Okay. Now you can please look at here. Now for this particular example, how many bytes are there in main memory? So there are 32,768 bytes in main memory. So these are 32,768 bytes in memory. So starting from byte 0, byte 1, and so forth, so on. Okay, now this is an arbitrary byte. This is actually byte number 20548, and this is byte number 20549. Okay, please remember. So now this is now. Please remember, all of these addresses are in hexadecimal. These are in hexadecimal address, and this is the address of the last byte. So can you see here? Okay, now how many number of memory blocks are there? So it is actually divided by the memory size. What is now the memory size? The memory size is now 32,768 and the block size is 64. So there will be 5.12 blocks in main memory. So we can partition this data into different blocks. So memory block 0. So the memory block 0 will now contain from byte 0 till byte 63. Memory block 1 will start from byte 64 till byte 127. And then there will be arbitrary memory block byte 321. It will start from byte number 20544 till byte number 20607. And how? Let's see. And please remember, now this is now my 15-bit address. Now this is my 15-bit address. If you look at here, this is a 15-bit address. So the tag field is 1010. The index field is 00001, and this is now the block offset field. If you convert this number into hexadecimal, if you convert this number, so it is actually, if you convert this number, please remember, if you convert this number into decimal, so this is the byte ID. So now can you see here? So this is, if you convert this into hexadecimal, this will give me the address, and if you convert this into decimal, it will give me the byte ID field. This is the byte ID field. Okay, this is just like the digital system now. Okay, now please remember now. Now if you look at this example, please look at this example. In this example, what we are doing? So this byte number 20548 now belongs to main memory block 321. So now how many sets do we have in this example? We have 32 sets. Main memory block 0 will be mapped here, block 1 will be mapped here. And please remember, main memory block 31 will be mapped to set number 31. What about memory block 32? Where 32 will be mapped? Help me. 32. Where 32 will be mapped? Please help me. In this example, we have 32 sets. No one is answering me. Yes, Insia. Farah.
Is it set 0 or what?
Yes. Why don't you speak early? Can you see? Main block 0 is mapped here. Block 1 is mapped here. Block 2 will be mapped to set 2, but set 2 is not shown here. We have 32 sets. And block 31 will be set here to map to set number 31. And then block 32, which is not shown here, will be mapped to set 0. 33 will be mapped to set 1. And block number 63 will be mapped to set number 31. What about block number 64? Block 64 will be mapped where? Where it will be mapped? Block number 64.
Set 0.
Set 0. 65, set 1, and so forth, so on. And block 30 will be 320 will be mapped here, 321 will be mapped here, and 351 will be mapped here, and so forth, so on. Okay, now how many memory blocks are mapped here? So it means there are 16 memory blocks can be mapped to a particular cache set. So to this set 1, block 1 will be mapped here, 33 will be mapped here, and then 33 plus 32 will be mapped here, and so forth, so on. So there are total number of 16 blocks which can be mapped to this particular set, and only 2 of them can reside in the set at the same time, because A is now 2 here. What will be the tag for the first block? Help me. The tag for the first block will be 0. The tag for the second block will be what? Help me. 1. And what will be the tag of the last block? Because there are tools for T tags, 16 tags. So the tag of the last block will be 15, which is actually 1111. What will be the tag of this block? The tag of this block will be 1111. Okay, now please remember. So in the previous example, so this we want to access byte number 2548, and it belongs to main block 31. So remember, this byte number 20548 belongs to main block 31, which is the 5th byte, which is byte 4 within the main block. And how do we do it now? So can you see block 1, block 2, block 3, and please remember. What will be the tag of main block 31? It will be actually 10, which is actually 1010. Okay, now please remember. This byte number 20548, which belongs to main memory block 321. And we explain it. To which set it belongs? We look into the set index field. Now this is my set index field. It's now mapped to set number 1. So we are accessing now set number 1. We are accessing set number 1. Okay. How many tags do we need to compare? 2 tags. Is it a hit in the first line or the second line in this example? Can you tell me? Can you see? Now we have this incoming. This will hit or the second line will hit? Anyone? Yes?
1010, the second.
Yes, 1010. So can you see here? It will hit in the second line. So it means that the block 321 is now found in the cache, and now it's a hit in the cache. Okay. Now we look into the block offset field. And we are accessing the byte 4 of main block 321, which is actually the 5th byte. So we are accessing the byte number 4 within the 5th byte. Okay, now this is another example. Please remember, now this is another example. Remember, this is another example. This is now example number 3. Now this cache consists of how many sets? There are 2 for 5 because now k is 5. How many sets are there? There are 32 sets starting from set 0 to set number 31. So there are 32 sets. How many lines are per cache set? How many lines are there per cache set? Tell me in this example. So associativity is 4 now. So now there are 4 lines per cache set. So this is cache line 1, cache line 0, cache line 1, cache line 2, and cache line 2. So there are 4 lines per cache set. Okay. How many bits are required for the tag field? So for the tag field, we need 7 bits per cache line. So these are the tag fields. Okay. Now, how many bytes are there within the block? So there is tools for B, which is actually there are 64 bytes per cache line because whereas B is to 6, so there will be tools for 6, which is actually 64 bytes per cache line. Okay. What is now the cache size? The cache size is actually computed by multiplying S with A with D. What is S here? S is now 32. This is because there are 32 sets. S is now 32. A is now 4 here, and now D. So there are 64 bytes in a block. So these are 64 bytes in a block. So this is, and if you convert this, it is actually 8192, and if you convert this into. And what's the memory size? The memory size is equal to 2 for M. What is M here? 18. So M is now 18. So this there will be 2 for 18 bytes. Okay, now let's zoom. Now we have this byte address. Now if you look at this byte address, so to which set it will go? It will go to set number 1 because now the set index is 00001. It will go to set number 1. And now we will compare this tag field with the stored tag field. Okay, please, it will compare it with the yellow. It will compare it with this pink color. This will with the white, and then with the brown one. Okay, now this tag matches now with which one? The first one, the second one, the third one, or the fourth one? Anyone? Yes. Anyone may answer? Now we are comparing this tag field.
The second.
Field. 1011010. Yes, it will tag with the second one. Can you see here? So it's a hit here. Now it's a hit here. So this is the second here. Block 1 is now found in the bed. Okay. Now what is the block offset field now? Can you see? Now we look at the block offset field. Okay. How many bytes are there in each block? There are 64 bytes. But now if you look at the block offset field, it is actually 000111. And it means we are accessing byte number 7 because now the byte index starts from 0. We are accessing the byte number 7, which is actually the 8th byte within that memory block. So what we are going to do, so now we are accessing byte number 7, which is actually the 8th byte within this particular cache. Any question? Any question? Should we proceed? Should we proceed?
Yes.
Okay, now how do we put in the data into the cache? Okay, now in this particular example, can you see here in this particular example? Now this is my memory. This is my memory, and now this is my cache now. How many main memory blocks are there here? There are 16 memory blocks. Block 0, block 1, block 2, until block 16. There are 16. And this is the block address 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now a direct map cache. In the direct map cache, associativity is 1. So each cache is set 0. It consists of how many lines? It only has one cache line. There's only one cache line in itself. Okay. Now, for example, on the right, there is a 16 block main memory. This is a 16 block main memory. And there is a 4 set cache, consists of set 0, set 1, set 2, and set 3. And each set has a single line. So we have a single line here. Okay. So main memory block 0, 4, 8, and 12 are mapped to set 0 now. Okay, they have mapped to set 0. What about 1, 5, 9, and 13? Yes, they are mapped to which set? Let's look at the color. All the blue color will map to set number 1. And all the green color will map to set number 2. And all the pink color will map to set number 3. And how can we compute this mapping? Now, how can we compute this mapping? I will compute this mapping. It's our division. One way to figure out which cache set a particular memory address should go to you, we use the mod operator. Okay, now if the cache contains 2 to the power k cache set, what is k here now? K is now 2 here. If k is 2 here, so we have 2 to the power k, we have 4 cache sets. Set 0, set 1, set 2, and set 3. We have 4 sets, cache set. And how we do compute it? So we compute it with the main memory block address mod 2 to the power k. Okay, now for instance, now here, if you, what is block number 6? Block number 6 is here. Okay, and then if we say we use it, the mod formula, mod 2k. What is 2k now? 2k is now 4. So 6 mod 4. You use the remainder operator or the modulus operator. So it means it will give us 2. So it means that this main memory block 6 is now mapped to set number 2. What about block number 14? If you look at here, so block number 14. So 14 in percent operator or the modulus operator mod 4 is now 2. Can you see here? So 14 mod 4 is now, it will also give me 2. Okay, now what we are going to do? We are converting all of these block addresses into binary. Please look at here. We are converting all of these addresses to block 00. It will be 0000, 0001, 0010, and blah blah blah. And this 15 will be 1111. You are converting all of these addresses into binary. So can you see here? We have 2 fields. Okay. Now we have an equivalent way to find the placement of the memory address in the cache is to look at the least significant k bits. So we need to look into the least significant k bits. So can you see here now? How do we know that block 14 is mapped here? So we look into the least 52 bits. So it means 10, and 10 it means it is now mapped to set number 2. What about block 6? If you look at the index field, now this is the index field, the least significant 2 bits. It means now it is mapped to set number 2. And the most significant bits are the tag fields. Now here, if you look at block 0, how many blocks are there in main memory? There are 16 blocks in. This is block 0, block 1, block 2. The other blocks are not shown. And now this is block 6. Block 6. Okay. Please remember. Now we have in the cache. Now we have the data in the cache. So can you see? We have the data in the cache. What is the tag for this? The tag for this is 00. The tag, it means that now block 0 is residing in the cache. So the block 0 is residing in the cache. Okay. Now if you look at here, set number 2. In set number 2, if you look at the index field is 10, and the tag field is 01. It means that currently block 6 is residing in the cache. Okay. What about set number 3? What is now the index field? Index field is 11. Index field is now 11 here. The index field is 11. And notice the tag field. The tag field is 01. So it implies that now block number 7 is residing in set number 3. Which block is now residing in set number 1? Can anyone tell me? Yes. Which block is residing in this set 1? Can anyone tell me which block? Anyone? First, we need to look into this index field. Index is 01. This is index is 01. And then we look into the tag field. What will the tag field for here? Can you tell me? What will the tag field here? Please answer me. Because can you see here? Block 13 is not mapped here. Block 13 is mapped here. What will be the tag for this? If block 13 is residing in set number 1, what will be the tag field?
11.
Anyone may answer? Yes.
Is it 11?
Yes, it will be 11. Yes. Can you see here? Block 13 is when, and then it will be 1. And how do we figure out? How do we figure out? Okay. Now, how do we figure out? So please look at the index field. So please look at here. The index field is now shown in red color. Okay. So in the red color for the first set, in blue color for the second set, in green color for the third set, and in pink color for the fourth set. Clear? So this is actually set 0, set 1, set 2, and set 3. So this is set 0, set 1, set 2, and set 3. Any question? Okay. Now can you see here? Now this is the tag field. This is the tag field. Now how do we get the main memory block address? The tag field is 01, and the index field is 11. So what is that now the tag field for here? The tag field is 0, 1, and the index field is 1, 0. And the tag field is now 1, 1, and the index field is now 0. And then how do we? Can anyone tell me? Okay, now here, this is a valid data or invalid data? Help me. The valid bit is 1.
Valid.
It's a valid data. And what's the memory block address? Okay, we look at the valid bit. Now this is my valid bit now. This is 0, 0. Sorry, the tag field. The tag field is now 0, 0. And what is now the index field? Index field is 0, 0. So the main memory block address will be 0, 0, 0, 0. What about this thing? This valid data or invalid data? This 0. Help me.
Invalid.
Invalid data. This is invalid data. This is now invalid data. Okay, now this is a valid data. What will be the address? Can you tell me the address? This memory block address. Can you tell me the address here? We should start with the tag and end
0,
with the
1,
index field.
1, 1.
Yes, 0, 1, 1, 1. So can you see here? So can you see here? This is 0, 1. This is the tag field, and 1, 1 is the now the index field. Any question? Any question? Okay. Okay. Now we are starting with the direct map cache. Please remember in the direct map cache. Okay. We assume we have the same with the same example. How many sets are there in the direct map cache? How many sets are there? Help me.
4.
4 sets. Okay. How many memory blocks are here? How many memory blocks are here?
16.
There are 16 blocks. So there are 16 blocks, and we want to map it into different sets. Okay. Now please remember. This is block number. This is the block address. Block 0. This is my block 0 now. The first block 0. Where this block 0 will be mapped. Yes.
Set 0.
Yes. So can you see if this is now the main memory block address, so it will consist of the tag field. So if we convert this 0 into binary, it will be 0, 0, 0, 0. If you convert this into 1 into binary, it will be 0, 0, 0, 1. If you convert this 2 into binary, it will be 0, 0, 1, 0. If you convert 3 into binary, 0, 0, 1, 1. 4 into binary, 0, 1, 0, 0. So let's assume these are different blocks at different time. Let's assume this block 0. Now we are accessing block 0 initially for the first time. We want to access block 0. It will be hit in the cache or missing the cache. Help me. Initially.
Miss.
Yes. Okay. Now this main memory block 0 will be mapped to which set? Look at the index bit.
0.
It will map to set number 0. Okay. Now when we map to main memory block 0, so the main memory block 0 now goes to set number 0. Okay. Now the tag field. This tag field will go here. This tag field will go here. Clear? Okay. In the next iteration, we want to access main memory block 1. Okay. Now please remember. Now block 0 already resides in set number 0. Okay. Okay. Now we want to access block number 1. Block number 1. Look at the index field. Where it will be mapped? Help me. Which set?
1.
It will go to the set number 1. And this tag will be this tag will go here. So it will go to set number 1. It will miss. When bring this block. So this is actually main memory block 1. So now main memory block 1 is now residing in set number 1. And the tag of the set number 1 is 0, 0. Okay. Now we want to access the block 2. To which set it will go? Anyone help me? Yes.
The 1, 0.
It will go to set number 2, 1, 0. It will go to set number 2 because now the set index is 1, 0. It will go to set number 2. And what will be the tag field? It's a miss. So now the tag field is 0, 0 because the tag is 0, 0. And now memory block 2 is now residing in set number 2. Again. Now we want to access block number 3. Where it will go? Help me.
Set number 3.
It will go to set number 3. and the block tag is 0 0 here. Okay, now the problem is this. Now we want to access block number 4. This is very important. Okay, now we block number 4. Okay, it goes to set number 0. Can you see? It goes to set number 0. But now the problem in set number 0 is that in set number 0, which block is now residing? Main memory block 0 is now residing in set number 0. And we compare the tag. We compare this tag with this tag. Does this tag matches or in matches? Doesn't matches.
Different.
It's different. So we need to kick out main memory block 0 and now bring main memory block 4. So in this case, we need to, it's a miss in the cache. So we need to kick out main memory block 0 from the cache and bring in the block 4. And if you bring the block 4, so it's mapped to set number 0. And now the tag field is updated. Initially, the tag field was 0 0. Now the new tag field is 0 1. Now it means that now at this point of time, block 4 is now residing in the cache. Any question? Should we proceed?
Yes.
Now, next time, in the next iteration, we want to access block number 3. We want to access block number 3. And because now block number 3 is already in the cache now. Block number 3. Block number 3 is now residing in set number 3. Can you see here? Now what is the index? So now index matches, it matches here. And now we compare the tag. So we compare this tag with this tag. Will it be a hit or a miss? Help me. This one and this one. So it means that now this
The tag is the same.
block number 3, it will be a hit in the cache. Why it will be a hit in the cache? Because it is now hit in the cache because it is mapped to set number 3. The index is same. Now we compare this tag field with this tag field and it matches, then there is a hit in the cache. In the next iteration, can you see here in the next iteration? Now we want to access block number 4. Block number 4. Okay, it is mapped to set number 0. Set number 0. We compare, okay, this 4 is already residing in the cache. We compare this tag and this tag. This tag matches or doesn't matches? It matches. So this matches, so it means there is a hit in the cache. And again, now block number 15. Block number 15. If we convert this 15 into binary, it will be 1 1 1 1. Now block number 15, it is mapped to set number 3. But if you look at set number 3, the main memory block 3 is residing. Will be a hit or a miss?
Miss.
It's a miss. Okay, because why is a miss? Because the tag does not match. So this tag does not match with this tag, so it's a miss. So we need to kick main memory block 3 and bring in main memory block 15. So it's a miss in the cache. We need to kick main block 3 and bring in main block 15. Any question? Any question? Should we proceed? So there are 8 requests and there are 6 misses. Okay. Now what is the problem with the direct map cache? So there is a problem with the direct map cache. Let's assume that we have direct map cache. In this particular example, how many sets are there in the cache? In this particular example, and can you tell me how many sets are there in the cache?
Four.
Please help me. How many sets are there in the cache?
4.
There are 4 sets. This is set 0, set 1, set 2, and set 3. Okay. So block 0 will be mapped here, block 1 is mapped here, block 2 is mapped here, block 3 is mapped here, and block 4 is mapped here. So both block 0 and 4 are mapped to the same set. So now the problem is that, so we initially, when we bring block 0 is now mapped to set number 0. So we put it here because now the tag is 0 0. But when we access 4, there will be a miss in the cache, and when we change, we kick out block 0 and then we bring the block 4 here. Next time we have access to block 0. When we have access to block 0, still okay. Now who is now residing in the cache now? Block 4. It will be a hit or a miss now from block 0. It will be a miss in the cache. Why there will be a miss in the cache? There will be a miss in the cache. It means now the new block is 0 is also mapped to set number 0, but it is evicting now 4. And let's assume in the next iteration we want to access block number 4. Whenever we want to access block number 4, it's also mapped to set number 0. And who is residing in set number 0? The main block 0 is not residing. It will also be a miss. So what's going on? So block 0 is evicting block 4, and block 4 is now evicting block. So this is the problem with the direct map cache. And now even, can you see here? Because this 0 and 4, 0 and 4, 0 and 4, all of them are mapped to set number 0. Even the other sets in the cache are empty, but we cannot fill them in other cache sets. The reason is that because of the block mapping policy. Any question? So the direct map cache causes a thrashing problem. We call it a thrashing cache problem. Even these seats are empty. Even these seats are empty. Since these seats are empty, these cache sets are empty. But since all of these two blocks are mapped to the same cache set, they will be vectoring with each other. Any question? So now summarizing my today's lecture, what is a cache? Cache is a small high-speed memory between the processor and main memory, and it stores a copy of the most frequently accessed data item from memory. And it improves the system performance by exploiting the spatial and temporal locality. What does spatial locality tells us? A spatial locality tells us that if we access an item now, it is more likely that we will access the next adjacent item in the near future. And so to exploit the spatial locality, so we not only bring the block, but we fetch the whole block to which a particular item belongs to. So we bring the whole block. And what is a classical example of spatial locality in data? The classical example of spatial locality in data are arrays. Because in arrays, if you are accessing A0, it is more probable you will access A1 in the near future. And what is the example of what does temporal locality says? A temporal locality says that if you are accessing an item now, it is more likely that we will access the same item in the near future. And what is the classical example of temporal locality? So the classical example of temporal locality are the loop variables, because the loop variable are accessed multiple times. So cache exploit the concept of spatial locality and temporal locality. And spatial locality says that if you are accessing an item now, it is more probable that we will access the adjacent item in the near future. And the temporal locality says that if you are accessing an item now, it is more likely that we will access the same item in the near future. And what does a cache contain? It consists of S sets. Each set consists of A cache lines, and each line consists of D bytes. And we partition the main memory block address M into 3 fields. One is the tag field, and then the index field, and the offset field. Any question? Any question? Yeah. Any question?